Hello and welcome to Unit 5 one more time. In this last part of Unit 5, we're going to do some more examples involving friction. The first is a continuation of an example we started in Part 1, where we have an object coming down an incline. In Part 1, we completed this part where we showed that the acceleration was g sine theta, assuming friction was 0. In this part, we're going to do the second part of this example, where we show that the acceleration takes the form g times sine theta minus the coefficient of kinetic friction cosine theta when friction takes the form F equals mu n. As before, we're going to have our incline. Here is our object. The angle theta is with respect to the horizontal. As we did in Part 1, we're going to cant our coordinate system so that x points down the incline and y points perpendicular to it. If we think about the free body diagram, we have the normal force between the ramp and the block pointing along the y-axis. We have friction that will point up the ramp along the negative x-axis, and we have gravity pulling downward. We can now draw the triangle where here is the horizontal. Let's try hypotenuse. The y component is again found using a cosine. Remember that in Part 1 we showed that this angle would be theta. And the x component is found using the sine. I can now apply Newton's second law in the two directions. In the y direction, because I canted the coordinate system, the net force is 0. I have two forces on the block. I have the normal force from the ramp on the block and the y component of the block's weight. They point in opposite directions, so I subtracted them. This tells me that the normal from the ramp on the block equals mg cosine theta. I can now look at the x direction. In the x direction, the block is accelerating. It is accelerating down the incline, which is the positive direction. So I'm going to take all forces in the positive direction. That would be the x component of the block's weight. Subtract off the force of friction and set that equal to the block's acceleration times its mass. I can now plug in that the x component of the block's weight is mg sine theta, and friction is going to be the coefficient of kinetic friction multiplied by the normal force. Using the value for the normal force that I found from the vertical direction, I see that I can cancel mass because it is in every term, and factoring out the acceleration due to gravity leaves me that the acceleration down the incline is g sine theta minus mu k cosine theta, consistent with the problem statement. The last example for this part involves a contestant pulling a block of ice across a frozen pond during some sort of winter sporting event. So in this case, we are going to be dealing with friction and forces in 2 dimensions. It makes sense in this case to use a standard XY coordinate system because our acceleration, if there is any, will be across the surface of the pond. I'm going to actually get rid of that arrow. Finishing out my drawing, the contestant is pulling on the block with a rope that is angled with respect to the horizontal. Again, looking at the table at the end of part 2, I see that for ice on ice, static friction equals 0.1 and kinetic friction equals 0.03. Drawing the free body diagram for the block of ice, I have a normal force from the pond on the block. I have the block's weight pulling downward. I have friction between the pond and the block. And I have a tension force from the rope on the block. That tension force, again, is angled with respect to the horizontal. So I need to divide it into components. Tension force is along the horizontal. The y component in this case will be found using a sine. Oops. And the x component is found using the cosine. Part A of this problem wants to know the minimum force he must exert to get the block moving. Well, the minimum force he must exert to get the block moving means he must just exceed the maximum value that static friction can be. Okay. Assuming he maintains whatever force he's pulling with, what would be the block's acceleration once it starts to move? In both cases, the net force in the y direction is 0. So that will be unaffected by whether or not it's static friction or kinetic friction. I have 2 forces. I take that back. I have 3 forces in the vertical direction. I have the normal from the pond on the block pointing upward. The y component of the tension pointing upward, and the block's weight pointing downward. This allows me to solve for the normal force from the pond on the block in terms of the y component of the block's tension and the block's weight. I cannot really plug numbers in at this point because I don't know what that tension is. That's what I'm trying to find in part A. For part A, we're dealing with max static friction. That tells us that static friction will equal the coefficient of friction times the normal force, which in this case, that tells us that FSB will equal mu S times, not S, let's try P, PB. So that would be mu S mg minus mu S TRB sine theta. And again, I can't really plug in numbers here because I don't know the value of the tension in the rope. However, I can use static friction to find that tension. Not static friction, sorry, the x direction. In the x direction, since we are dealing with static friction, it is not accelerating. I have 2 forces. I have the x component of the tension minus the friction in opposite directions, so I subtracted. So TRB cosine of theta minus mu s mg minus mu s TRB sine theta all has to equal 0 newtons. This allows me to solve for TRB, factoring out TRB times cosine theta plus mu s times the sine of theta will equal the coefficient of static friction times the mass times the gravitational acceleration, and I can plug in values at this point. Mu s for static friction was 0.1. The mass was a 45 kilogram block. Acceleration due to gravity is 9.8 meters per second squared. And we're going to divide by the cosine of 25 degrees plus 0.1 times the sine of 25 degrees. And that works out to be 446.49 newtons. For part B, the block is accelerating. The setup for the x direction is the same. The only difference is that instead of static friction, we're now dealing with kinetic friction, and the tension we just found in part A is the tension the rope is being pulled with. So that allows me to write that TRB times cosine of theta minus mu k sine theta minus mu k mg will equal ma. Solving for the acceleration will equal 46.49 newtons times the cosine of 25, no, not 45, sorry, 25 minus 0.03 times the sine of 25 minus 0.03 times 45 kilograms times 9.8 meters per second squared. All of that divided by the mass, 45 kilograms, and that works out to be 0.66 meters per second squared. Okay, so again, for part B, we move from being static friction to kinetic friction. So if I look at this line of part A, everything that was a static friction coefficient becomes a kinetic friction coefficient. The other assumption for part B is that the tension we found in part A is maintained once the block starts moving. So since we pulled at 46.49 newtons to get the block to move, we're going to continue pulling with 46.49 newtons. This concludes this part of Unit 5. It also concludes Unit 5.